Hi, everyone. I'm Rochishnu Chowdhury. I'm a postdoc in ANAG, and thank you for coming to my talk. So the title, like the previous speakers, it's a bit long. I would try to take your attention to three words here: ternary alloy solidification. So with the first slide, I'll try to explain why should we study alloy solidification. It helps us understand microstructure formation. And during a solidification process like casting, the solid-liquid interface goes from a planar structure to cellular to columnar and then dendritic. And these structural changes affect the mechanical properties of your alloy. And understanding this process can help you better design alloys with certain custom mechanical properties. And also you can prevent defects by a thermal management. So next, keyword in the title was ternary. We are trying to develop a system that can deal with three component, also known as ternary system, and even more than that. Figure 2, kind of at the bottom, kind of shows the equilibrium phase diagram of the three metal components in the system as a function of temperature and the metal composition. And we can see how complex a phase diagram like this is. And so understanding this helps us understand the solidification process better. With that, now, how do we model such a complicated approach? In the continuum world, you can do it in two ways. One is the diffused interface, one is the sharp interface. Diffused interface, as the name suggests, your interface is of finite thickness, and this is artificial. And so it leads to certain numerical artifacts. We want to avoid that, so we are going for the sharp interface approach, where you have a sharp transition between your solid and liquid, and we preserve the discontinuity that's present in the concentration fields in your system. So with that modeling choice, there are certain difficulties that come with. We first have to keep track of a moving front, which is your solid-liquid interface. Then you have to impose certain boundary conditions in a sharp way at the interface. And then you have to solve 2n plus 6 fields. We want to develop a general solver for an n-component alloy system. So you have scalar fields in the solid and scalar fields in the liquid. Two of the velocity components in a two-dimensional system, temperature in the liquid and solid, and two other scalars that help you determine the interface position, and one for helping you in the fluid solver. With that, I would like to draw your attention to certain interesting physics that's going on in this process. And a lot of it happens at the interface. First, you have the thermal balance at the interface, where the jump in the thermal gradient kind of gives rise to the interface velocity. That is known as Stefan condition. Then you have nonlinearity that's introduced by the Gibbs-Thomson relation, where the liquid temperature at the interface is a function of all the metal components that you have. It's also dependent on the normal interface velocity and the curvature of the interface. Then you have discontinuous concentration fields across the interface that are connected by chemical equilibrium and solute rejection equation. With all that, you have also the velocity fields moving around moving along the solute in the liquid domain. So this is all the complicated physics that we need to solve. What does a solver like this look? So step one, we have to solve for the scalars. And for that, we solve advection diffusion reactions. The advection part is treated explicitly using semi-Lagrangian methods. And then the implicit part, which is stiff, the diffusion, which is stiff, is treated implicitly. For a two-component alloy system, it's much simpler. You can just use a Newton iteration method to deal with the nonlinearity. But when you go from 3 to more, it becomes complicated, which is the novelty kind of in this solver. You have to develop an adjoint system and make sure you simultaneously solve the system equations in a way that you satisfy the concentration boundary condition as well as the temperature boundary condition. So when you have these scalars solved, you extend these fields across your front, across the discontinuity by PD extrapolation methods. Then you calculate the interface velocity from your Stefan condition. And then once you get the interface velocity, you get the boundary condition for your fluid solver. So you solve the fluid for the next time step, and you advance your interface under this new interface velocity. You refine and coarsen the grid so that you have maximum refinement close to the interface. Then your time step ends and you go on to your next time step. So I mentioned adaptive grid. It is very necessary for a problem like this. The most interesting physics is happening very close to the interface, so you need maximum refinement there. If we had that level of refinement throughout the grid, this simulation would be too expensive to run. So the method that we use to identify our interface is an implicit way of doing it. It's the level set method introduced by Setyan and Osher in the 90s, where the zero contour of a higher dimensional function essentially determines your interface. And we use this approach on adaptive quadtrees using the pforest library. Details, you can look at the paper by Karsten. So here is a simulation of directional solidification of dendrites happening in the presence of a thermal gradient along with a shear that's present at the top of the domain. Okay, to compare kind of the effect of convection, we also ran the same case in a no convection situation. So, next slide. Wait. Okay. Yeah, here. So here I show that we do capture the effect of the convection in between the dendrites. As you can see, the solute is being carried away from the right-hand side of each primary dendrite to the left-hand side, which gives more material present in the left-hand side of each primary dendrite, leading to faster secondary dendrite growth on that side. And then to the right, if you overlay the dendritic structure of a convection case and a no convection case, you see there is a clear difference. The blue outline kind of refers to the convection case, red outline refers to the no convection case. So dendritically, structure-wise, there is a clear difference. Now, I also plot the concentration of two of the metal components, tantalum and aluminum, in this three-component alloy system. And you can see we can resolve the gradients of the concentration even inside the dendrite. And again, inside the dendrite, there is a difference in concentration between convection and no convection. And although the color from the color scheme, the two concentration kind of look the same, but bear in mind the order of magnitude is different. So there is a difference. And the third concentration in this three-component system is 1 minus sum of these two scalars. With that, we also want to know if such a complicated solver is convergent. So we use a method of manufactured solution to understand if we increase the refinement, is our error decreasing? Yes, it is, and we get first order accuracy. The reason is all our scalar equations are second order, but our fluid solver is first order because we need to do certain interpolation between the nodes and the phase centers in our grid because the fluid velocities are present in the phase centers and the solute and the other scalars are present at the nodes. With that, I want to talk about certain areas of improvement that can be done in this solver. Firstly, if we can fully transition to a node-based solver, that means moving the fluid solver from a MAC grid with where the fluid velocities are present at the faces to a node-based solver, then you can get, we believe, full second-order convergence along with second-order gradients, which would be great. Then we want to add support for nucleation to cover a wider range of phenomena. What is nucleation? Apart from the dendritic growth that's happening from the soil liquid front, you can, under certain conditions, you can have grains growing from inside the melt pool. So you want to also capture that. Then finally, it would be great if we can extend this solver to 3D. This will be expensive as you already see all the different steps that are present here. With that, I would like to thank all my colleagues, my advisor, Frederic, in UCSB, and my advisor, Hans at LBNL. Thank you for coming to my talk.